So as we said, carbon is one of the elements of life. If you are old enough, you may have heard that there are certain elements which are called the elements of life: carbon, nitrogen, oxygen, phosphorus, sulfur, hydrogen, and so on. Carbon is a critical one because all the hard structures of plants and animals and us, they are made from some carbon-based compound, right? So long live carbon. Let's go back 500. Oops. Sometimes when I try to bring up the laser pointer, things jump. So let's go back 500 million years in time, a long time ago. In fact, half a billion years. The Earth is celebrating its 4 billionth birthday, and the trilobites have been invited to the party. It's been warmed up quite a bit along the way since Earth was a snowball. The snowball disappeared and we are warm again. All kinds of new forms of life are developing in the sea. Strange creatures with eyes on stalks and wacky feelers, tentacles and so on, funny little trunks and mean looking spikes and complicated tentacles. But above water there is absolutely nothing going on, still just rocks and lava. There is not a living creature to be seen anywhere, not even a tiny clump of moss which can grow on a rock. So you can see here some weird looking animals with spikes and whiskers and some hard structures and leafy looking things and something with a thing sticking out and so on and so forth, along with our trilobites. And these were all underwater, but then very cautiously the first plants start heading out onto the land. This could have happened because plates were moving and the sea level dropped on one rock, and then suddenly some little algae was sticking its head out of the water on land and saying, "Oh my God, this is something new. I have never been out of the water before." Right? The air is still packed with CO2 though, but that's handy for plants because they need CO2 to grow. Just like bacteria, they use sunlight and water to make carbohydrates out of CO2. Carbohydrate is basically a sugar, and then they make leaves, twigs, branches and fruits out of the carbohydrates, and the oxygen that is left over from all this disappears back into the air because it's not dissolving in the water where you are moving around, it's going into the air, right? So using this method, the plants slowly conquer the world. They got little algae or bacteria, then it says, I need to stand up, so it makes some hard structure, right? Like leaves, it needs to capture sunlight, and it needs twigs like these to grow more leaves. They are like the solar cells, right? And then they make branches and fruits, and you have to think about flowers, seeds, fruits. We are just jumping everything and saying fruits, but pollinators would have come along and so on and so forth. So lots of nice evolutionary detective work has to happen. Using this method, the plants slowly conquer the world, popping up all over the place and growing like crazy. Suddenly they found all this nice hard structure, land where they can just start growing and moving, and seeds flying around, flowers flying around, and so on and so forth. This means with that less and less CO2 goes into the air because everything is going into carbohydrate, and more oxygen is getting into the atmosphere, and that makes the world above the water suitable for animals too. So I already mentioned pollinators, but as you began to build oxygen, maybe other forms of life began to evolve, and these are obviously, we are saying in a very simple way. When you grow up, you will read more and see how complicated that whole story is. But there are no dinosaurs or mammals yet, but there are giant insects and other big scary critters. Dragonflies were maybe 2 feet wide because there was so much oxygen and there were nobody to eat them, so they could fly around slowly. If there is somebody who comes along and says, I'm going to eat you, then you have to move quickly, in which case you would probably become smaller so that you can move quickly, right? How would you like to meet spiders as big as a meter across, dragonflies with wings of half a meter, and centipedes that are longer than people? Well, if you're scared of these insects, then don't worry about it. We're just imagining the past, and there is evidence of such big things. Animals need carbohydrates to grow and as a source of energy for them to move around, to reproduce, live long, and so on. So on. They eat plants to get their dose of carbohydrates. They breathe oxygen so they can burn the food they consume and produce energy, not on a fire but inside their bodies, just like you and I, not on a fire at all. During this burning process, CO2 is released. We are always releasing CO2 and breathing in O2. The animals breathe it out, CO2, and the plants put that CO2 to good use. So we are all symbiotic. We do something, they do something, and so on. But now we are cutting down trees. This means that carbon is always moving from place to place. It is in the air, in the plant, in the ground, and in the animal, in the water. It mixes with all kinds of other little particles, dust and rocks, and together with oxygen it forms CO2. With hydrogen it forms methane, and with oxygen and hydrogen it makes carbohydrates. You write your photosynthesis equation. 6CO2 plus 6H2O gives you C6H12O6, which is carbohydrate, right? With hydrogen it forms methane, and with oxygen and hydrogen it makes carbohydrates. No living creature can do without it. If you divide your weight by 5, you will find how many kilograms of carbon are inside you. We are mostly water, but we are also a lot of carbon. When people, animals, and plants die, the carbon is released into the air again. This happens because they rot and decay. Bacteria and molds break everything down. Try leaving an apple or a sandwich on a plane for weeks. You will see and smell it as well, the change for yourself that you can feel when also people eat. And that word we used before, fart. Eventually what is left of the carbohydrates is carbon and oxygen. So we synthesize it into organic matter, we consume it and split it back into inorganic matter like carbon and oxygen or CO2. This rotting process requires lots of oxygen, though. If there isn't much around, the bacteria are unable to make any CO2, so they turn the carbon into methane instead. Because they cannot photosynthesize, they do some other ways, fermentation like thing, to produce energy, which is made up of carbon and hydrogen. So it is, for those who know enough chemistry and older, that's called a reduced form of carbon as opposed to CO2, which is the oxidized form. But if there is no oxygen around, bacteria and mold cannot get much done. Consider, for example, what happens when a plant falls into the water. Back in the days of the big scary critters, there was a high chance of plants falling into water, as lots of plants and trees grew in swamps. Think of the swamp monsters. But if you're scared of monsters, don't worry. In a swamp, no oxygen can get in to the dead remains of the plant, so the plant doesn't rot and the carbon disappears deep into the ground. If carbohydrate falls and nobody is eating it, it just remains carbohydrate. More falls on top, keeps getting compressed and becomes peat, and then gets into the ground and becomes coal, and so on and so forth. For hundreds of millions of years, trees and plants disappeared into the swamps. All their lives they had taken CO2 out of the air, and now they took it with them under the ground. So CO2 slowly disappeared from the air, and less CO2 means less heat in the air. Ice caps grew again at the North Pole and the South Pole, but this time the planet did not turn into a snowball Earth. The cold stayed near the poles. Between the poles there was good deal warmer as climate and ocean, atmosphere, land, everything remained warmer. Just like now, there were lots of different climates on Earth. You had freezing poles, and then you had temperate climates, boreal climates, subtropical tropical and tropical climates and so on and so forth. So CO2, oxygen, carbon, dead animals and plants and everything was going on. The biological movement of carbon, the inorganic or chemical movement of carbon in the water, on land, through the animals, through the insects, and so on and so forth. Okay, so we'll come back and jump forward to the time of the dinosaurs, which lived from about 250 million years ago to 65 million years ago. What finished them off? You already heard this story many times, but we'll go through it again just for fun. Okay, see you in the next podcast. I hope this is fun. I love reading it, and I'm talking like I'm talking to a kid, and hopefully if you're older you are not thinking, why this grandpa talking like this? So see you next in the story of the dinosaurs.